Welcome to Hot Chips 2025. Session 4, Networking.
Hello, everyone. We are having the last section of the day, networking. We have 4 presentations for this section. After each presentation, we will have a Q&A section. And you can also submit your questions through the Slack channel. Our first presenter is Pat Fleming, and he's going to present the 2nd generation Intel Infrastructure Processing Unit. Pat is a senior principal engineer with Intel's Network and Edge group. Pat leads the silicon architecture for the Intel's connectivity products. Pat lives in Ireland and loves this opportunity to visit sunny California. Welcome, Pat.
Thank you, Larry. Thank you all, and thanks, Sherry, and thanks to Hot Chips here for the opportunity to present today. I also like to thank all of my colleagues for their contributions to this product. Many of them in the labs today, testing and characterizing the silicon. So today I'm here to present Intel's 2nd generation infrastructure processing unit, known as the IPU. And I've got the clicker right. So today, when we look at data center networking, we're certainly living through one of the most transformative periods of the industry. It's a time when we're operating where the very definition of the data center and the data center network is dynamic and constantly evolving. The key word being dynamic in this space. The large cloud service providers, they don't and can't wait for standards to emerge and evolve. Instead, they build custom stacks with their own innovations around transport protocols, scheduling, telemetry frameworks, orchestration layers. Many of the innovations we see in open networking and programmable fabrics start in the large hyperscalers and trickle down to the standards bodies and the broader ecosystem. This creates the need for intelligent programmable infrastructure that allows the data center network to adapt and evolve even faster than silicon cycles allow in a lot of regard. And I guess my reality check was when I tried to use an LLM to help me write this intro, and it was completely out of date already. So the Intel IPU is architected with adaptability and programmability from its core with performance, designed to meet the explosive demands of data center networking with flexibility, supporting diverse workloads from AI clusters to storage to virtualized network services, ensuring every node in the data center is optimized and future-proof. So just briefly to recap on what we refer to as an IPU, the Infrastructure Processing Unit, and then I'll deep dive into some of the details of the product and the improvements gen over gen. Traditionally, the host CPU runs customer workloads, the virtual machines and applications, and also handles all of the infrastructure services like storage, virtual switching, encryption, firewalls, and such. As we scale up these workloads, like AI, as the density of tenants on this compute scales up, this model just doesn't scale. Those infrastructure services consume significant CPU compute resources. The IPU solves it by offloading the infrastructure functions off the CPU onto a dedicated programmable processing unit. The result is a much cleaner separation. The host CPU is left fully dedicated to customer virtual machines and applications, while the IPU manages data center fabric services, allowing both to scale more efficiently. That gives us higher utilization of compute, deterministic low latency, performance for workloads, and stronger security boundaries at scale. The key to success of this is providing flexibility for customization and performance. The IPU is made up of 2 major subsystems, the network subsystem and the compute subsystem. These subsystems are tightly integrated around a shared system-level cache backed by LPDDR memory. The tight integration allows the IPU to deliver custom high-performance data pipelines. The IPU can be viewed as a unified P4 programmable platform that can be tuned and adapted to meet the networking needs of the data center. The Intel E2200 adds significant capabilities above our prior generation, the E2100, doubling end-to-end network processing performance to 400 gigabits per second, providing 2x increase in memory bandwidth and increased core compute capacity, with 112 gig SerDes across 4 Ethernet ports and 32 lanes of PCIe Gen 5. One of the critical additions to the E2200 comes from seeing the need of platform flexibility across many different nodes in the data center. In that, the E2200 adds significant capabilities around PCIe I/O configuration. It includes 32 lanes of Gen 5, which can be bifurcated to support up to 4 Xeon hosts or even up to 16 endpoints, and includes a very flexible PCIe switch configuration. These improvements ensure that the IPU can scale to meet current workloads and adapt across future data center infrastructure needs. So just to get into some of the details of each of the subsystems, starting with the network subsystem. The network subsystem includes components required for packet processing and control, from the external host pins to the networking pins, the 400 gigabit network pins. The E2200 has been upgraded to support 400 gigabits of network throughput end-to-end. And to meet those diverse needs across data center platforms, it adds that flexible connectivity supporting 32 lanes of PCIe Gen 5. Those devices can be made up of 4 host 16 endpoints with many configurations in between. And for data center scaling of AI, high-performance compute and storage workloads, the E2200 includes support for Falcon's reliable transport for at-scale low-latency RDMA. It provides an NVMe device interface with inline offloads from the host. It provides packet processing pipeline, which offers extreme flexibility for P4 programmable pipeline with advanced per-flow shaping, quality of service, and telemetry to support the 400 gigabits pipeline upgrade across the device. The high-performance hardware-based inline crypto becomes table stakes for high-performance data plane security. The E2200 implements IPsec and PSP security protocol. On the compute side, the compute complex, which can be used to run all of the data center infrastructure applications, has been upgraded to support a larger compute capacity. That allows infrastructure services like storage initiator backends, TLS proxies, vSwitch, or even using it to create custom data pipelines across that tightly integrated system-level cache between the network processing pipeline and the compute complex. The 24 ARM N2 cores give lots of flexibility and capability around those infrastructure workloads. And as well as that, doubling the memory bandwidth capabilities with that 32 megabytes of system level cache and 4 channels of LPDDR at 6400 megatransfer per second. Within the compute complex, there's also the look-aside crypto and compression engine, which shares lineage with our Intel's Q80 engine, but has been upgraded to support new algorithms and custom DMA pipelines specifically for the IPU. For infrastructure offload, platform security becomes crucial. The management and security complex of the E2200 provides support for the internal and external root of trust and secure boot capabilities. To give an idea of the needs around the data center platform and the various nodes that's deployed, the data center itself encompasses a wide range of platform configurations, from compute-dense CPU servers to storage servers, network servers, and of course AI clusters. To ensure the IPU can operate across all nodes of the data center, platform flexibility was critical. The E2200 provides this flexibility through its host fabric and highly configurable PCIe hierarchy across those PCIe lanes. It can expose acceleration capabilities of the IPU to multiple hosts, ensuring full security isolation while doing so. In the multi-host example here, the IPU offloads infrastructure tasks from up to 4 hosts simultaneously, supporting applications such as vSwitch and proving a fully virtualized network offload pipeline. Each host is its own independent, fully isolated IPU, providing complete infrastructure offload and isolation along with it. In the headless configuration, the IPU can support up to 16 endpoints. The IPU's network and compute subsystem can be used to terminate the network transport, offload tasks such as encryption and compression, and run the complete infrastructure application, avoiding the need for a separate host CPU. The converged node shows a case where the IPU can be used to support both hosts and endpoints. For example, the IPU could be configured to expose a PCIe switch to each connected host, and with other devices such as GPUs or SSD as downstream devices on that same switch. The internal ARM cores can operate both as downstream PCIe devices to the switch, or they can operate as upstream devices on top of those switch, exposing the internal device acceleration to those ARM cores. This type of flexibility allows the IPU to support many connectivity and data transfer models, supporting low latency and secure and predictable data transfers between connected hosts and devices. For example, between the network, direct network connectivity to the GPU or GPU to network connectivity through that topology on our host fabric. So the GPU at its heart, the E2200 at its heart has been designed to meet the needs of multiple nodes in the data center across those platforms. At the heart of the network subsystem is the FXP packet processor. The FXP packet processor provides extremely flexible hardware-based P4 programmable packet processing. The packet processor is backed by the shared system-level cache, shared with the other components of the network pipeline as well as the compute complex. The E2200 provides 400 gigabits of performance, but the packet processor itself is provisioned to process a packet every cycle and can be configured to perform multiple pipeline iterations or passes per packet. It can implement many P4 pipelines simultaneously, supporting millions of flows across those pipelines and maintain performance and latency predictability. The key to the FXP packet processor is hardware configurability. It maintains low latency, high performance, but gives that flexibility and configurability across all nodes. The pipeline consists of many advanced and programmable hardware functions, such as the parser, which can support custom header formats and advanced processing of multiple header layers per packet. In addition, other functions such as the exact match, wildcard match, longest prefix match, etc., allow the implementation of complex processing pipelines to be built in the FXP. For example, an initial pass on receive may process the outer header layers, performing, say, tunnel endpoint classification, the implementation of access control lists, routing updates, and decapsulation of the tunnel. A second pass of that packet could then implement inner processing of a firewall and connection tracking with the application of metering, shaping, and receive side scaling to the host processor. There are endless examples, but the flexibility and performance of this pipeline, which is at the heart of the E2200, is second to none and has been proven across many workloads and use cases. Taking a closer look down the pipeline at the inline crypto block, the inline crypto block and its capabilities include a hardware-based programmable engine providing security protocol processing for data in transit through the pipeline. Similar to FXP, the parsing and classification can be configured, supporting many header formats and layers. Because of its hardware pipeline, it implements extremely low latency security for the data plane. The engine implements full termination of both IPsec and Google's PSP protocol and can implement the protocol simultaneously across different flows. The E2200 inline crypto has been scaled by 2x to support 400 gigabits per second, and it now supports 64 million flows per direction and includes the addition of AES as well as Chachapoly algorithms within the engine itself. On top of encryption and decryption functions, the inline crypto engine implements all of the functions needed for IPsec or PSP protocol. Functions such as packet integrity checks and authentication, anti-replay window protection, sequence number generation, the packet header modifications, encapsulation and decapsulation, the statistics gathering, error checking and reporting, all associated with those security associations that are passing through the data plane. The inline crypto engine maintains the security association database and control for all security offloaded flows. The database is again backed by that system level cache and can back out into LPDDR of the device, and it can be virtualized to ensure security association and isolation across all of the flows of the system. As we back the security associations out to external DDR, we maintain those encrypted and isolated across our virtualized services. The traffic shaper. So in general, the IPU provides extremely fine-grained per flow quality of service. This you'll see through all of the components in the pipeline that we support very fine-grained per flow services. The E2200 supports two modes of operation. The first is data center bridging capable network arbitration mode, scheduling packets across a multi-level hierarchical scheduler, including source port, egress port, and traffic class. The second mode is our timing wheel mode, supporting per flow pacing of packet flows, where pace is either determined by the software stack or by rate policies as configured and enforced by FXP classification rules. The timing wheel enables a pacing resolution of 512 nanoseconds per slot. And similar to other processing components of the network subsystem, the traffic shaper is backed by system level cache, where it's used for buffering of headers until it achieves that slot in the timing wheel. Flow quality of service and resource usage is configurable with quotas, actions configurable per flow. The RDMA transport engine of the E2200 is critical for any data center networking device. The RDMA transport engine provides an IB verbs interface to software, which could be running on the external host CPUs or the internal ARM cores. The RDMA engine is capable of supporting up to 2 million queue pairs across multiple hosts simultaneously, with up to 1K virtual functions supported on a host. The engine ensures resources and VM isolation. It provides low latency, high reliability using Falcon Reliable Transport Protocol, ideal for use cases such as scale out of storage or AI workloads. Falcon provides delay-based congestion control supporting selective ACK and hardware-driven multipath capable connections for scalability and maintaining ultra-low tail latency. Falcon Transport can bypass the packet processing pipeline for latency optimization and makes use of the existing inline cryptography block to implement low latency, high rate, high-scale PSP encryption, and takes advantage of the traffic shaping to implement the per-flow traffic shaping. The transport engine comes with best-in-class Swift congestion control algorithm with optional programmable rate updates. And to ensure ease of deployment and efficiency, it includes flow isolation with fine-grained telemetry and statistics. In the compute complex, I covered the existence of our look-aside crypto and compression engine, the LCE component. LCE, as I said, was originally derived from Intel's Q80 engine, and over the past two generations of the IPU has been optimized specifically for IPU use cases. In a similar manner to the RDMA engine, LCE can be virtualized and exposed to multiple hosts simultaneously. Those hosts can either be the internal ARM cores as a host or one of the 4 externally connected Xeon hosts. LCE includes many services, and one of its most powerful capabilities is the ability to chain those services together in a manner custom to any given deployment. So the DMA engine provides the ability to offload data movement to and from different host address spaces, remote host to local or vice versa, with security and address isolation checks embedded. The DMA function also incorporates a programmable engine capable of performing custom checks and payload transfers while completing those data movements. LCE includes cryptography and authentication for storage and networking flows. It implements industry-leading Z-standard compression and decompression with support for large decompression history buffers of up to 16 megabytes. The E2200 provides additional bandwidth for DMA on top of previous generations and adds asymmetric crypto as an offload service, with RSA and ECC for acceleration of applications such as TLS. On top of Z standard and snappy compression, the E2200 also adds industry-compliant deflate compression and decompression, providing backward compatibility for storage applications and such. In the data center, integrity of data is paramount. When performing offload transforms, it's critical that we guarantee recoverable data. To this end, LCE implements an encrypt and verify function, as well as a compress and verify function, which guarantees the recoverability of all data after transforms. So any data that goes through an encryption transform or compression transform is verified with the reverse transform before committing that data outside of LCE. LCE also includes CRC generation, verification, and hashing capabilities. And all of these capabilities come together along with that system level cache, the compute cores, and our networking pipeline to allow us to be able to build very custom flows across all of these engines for the IPU. The following pipeline provides an example of the configurability offered for infrastructure offload with the IPU. In this example, the IPU exposes an NVMe device to the host software. Software running, for example, on an external host. That software could issue an NVMe write. The NVMe engine enqueues and schedules the event to the ARM cores, which act as an orchestrator and in turn process the NVMe request and initiate the movement of data from external host memory to our local memory of the IPU. While performing that data movement, LCE can be used to compress and encrypt the data inline without any additional data copies. Before LCE signals completion of the transforms, it performs a reverse transform to guarantee data integrity. The ARM cores are then signaled of the completed data movement and complete the necessary functions of the NVMe transport stack before performing an NVMe over fabrics transfer using the RDMA engine, in this case Falcon's reliable transport. The E2200 with its high throughput, low latency network pipeline, extensive compute and that shared system level cache and critical acceleration capabilities accompanied with hardware configurability provide extreme adaptability across these nodes, along with performance to meet the needs of that data center at scale. Again, to recap somewhat on some of the aspects we said in terms of deployment across various data center nodes, the IPU increases infrastructure security and isolation by enforcing an air gap between the customer applications and those infrastructure services. By moving infrastructure tasks like virtualization, management, storage, and networking onto the IPU, the infrastructure becomes securely isolated from tenant applications. On the other hand, IPU also saves host cycles by offloading the data center infrastructure, as well as providing acceleration offload for the VMs left on the host. So those VMs left on the host can be securely isolated from the infrastructure and still receive the acceleration benefits of the devices on the IPU. It significantly improves scalability and efficiency of the infrastructure due to the specialized capabilities and architecture of the IPU. But the IPU can also be used to improve those remaining VMs' efficiency on the host by providing that acceleration offload. The IPU is also uniquely suited to scaling out packet processing and distributed network functions at scale by potentially deploying multiple IPUs. For example, across a single Xeon host head node or operating multiple IPUs in a headless mode with an Ethernet switch. This can offer complex packet processing at high performance while delivering deterministic latency. In headless operation, the IPU can be used to simplify platform design and boost efficiency. By consolidating the full workload, the management of storage devices and accelerators such as GPUs, along with the PCIe switching onto a single device. In summary, the E2200 IPU provides the capabilities, adaptability, and performance efficiency to meet the needs of the constantly evolving data center infrastructure. Thank you for your time.
Thanks, Pat.
Thanks, Sherry.
Now we can start the Q&A section. Shall we start with the Slack channel first?
Sure.
So we have this question from Christoph Nowak. Why does the IPU use ARM Neoverse cores and not Intel's own E-cores?
Yeah, per product, we choose the most suitable IP based on constraints, time to market, and form factor. So for this particular product, based on power, performance, scalability, time to market, we choose the IP that's most suitable for that product. And that goes for all of our products.
Okay, start from here. Please give an intro for yourself.
Hi, Jeff Smith. Thanks for the talk. It's really nice to see you guys adding Z standard, actually. Can you share anything about particular use cases that pushed you guys into adding that? And also, are you able to share the window sizes or compression or levels of compression on the compression side as well as the decompression window you already mentioned?
Sure. Yeah, I guess Z standard is a leading edge in terms of compression ratio and performance across much of the data center. Now, Z standard leads the way in that regard. Deflate is still needed to support legacy applications, and you still need to be able to decompress that data. But Z standard across all benchmarks for those type of data center and database workloads, performance and ratio just is leading edge. Our implementation has been in close collaboration with our customers and such, and there's many tools and tricks that you can play in compression to improve that ratio. We believe we have the leading edge IP in this regard. On the compression side, this particular IP has a 256 kilobyte history buffer or window for compression, and as I said, on the decompression side, it's a 16 meg decompression history buffer window.
Thank you very much.
This side?
George Kozner from Chips and Cheese. Two questions, one real quick. What node is this being fabricated on?
Sorry?
What node is this being fabricated on? So what's
TSMC N5.
And so is there any additional encryption or compression throughput for local NVMEs beyond just or will 400G line rate consume all of the blocks?
I'm not sure I caught the NVMe part, but...
so if you have local NVMEs, is there any additional encryption or compression capabilities beyond just the 400G line rate?
So there is additional capability. So you get 400 gig for network data plane encryption across IPsec or PSP. For storage crypto, we have the LCE block, which does XTS and can also do all the other variants of AES and such for storage. So you get that additional crypto capabilities through LCE.
Okay, thank you.
And it can operate on both the initiator and target side for storage.
Awesome. Thank you.
Question from Slack?
Yeah, this question is from Robert Williams. Can you comment on the power envelope and cooling options, and what's the strongest use case in GPU networks?
Was the last question?
The use case in GPU networks.
GPU networks. Yeah, so power envelope based on, so because this is a in-packaged LPDDR device, power envelope depends on the configuration of the device. So the device operates in these configurations up to 75 watts TDP based on close to our highest configuration of the device. In terms of AI use cases, the most dominant use case for this device for AI has been on front end of AI clusters. But because of the reliable transport and Falcon reliable transport, it's also used for scale out of AI systems. So the front end of AI systems connected to storage and coming in, but also scale out of those AI systems on the front end.
This side?
Hi, Jun from Hawaii, Canada. So can you elaborate some features of E2200 which are specifically designed for AI application?
Yeah, I guess particularly for the, as I said, the RDMA Falcon reliable transport for scaling out of applications like that at high scale on lossy networks. So the use of selective ACK and multi-pathing through the Falcon reliable transport. There's also the case that our timing wheel support through our QoS and scheduling algorithms, as well as the crypto paths of PSP. The unique thing about some of those capabilities versus maybe some alternative implementations of that are not targeted specifically at AI is, in our case, they support extremely high number of flows and maintain state for an extremely high number of flows. So with that system level cache, can maintain very high performance and latency for those same flows.
Okay, thank you.
Any online question?
Yeah, maybe a couple. So this question is from David, but what is the processing latency for the packet pipeline? And maybe a related question, do you support customizing RDMA protocol?
So first part of the question, I think we should take it off into a deeper dive. The first part of the question sort of depends on what we're doing in the packet pipeline, to be honest, and how we've configured it and what the end-to-end pipeline looks like. So, you know, there are cases where we can bypass parts of the pipeline, cases where we pass the whole pipeline. So we should take that off maybe and have a deep dive on it. The second part of your question was?
Customizing the RDMA protocol.
So customizations, yeah, so we support RDMA over Falcon, this product. There's customizations involved in terms of you can use programmability for things like flow rate updates and such of that pipeline. But yeah, beyond that, it's a RDMA over Falcon is our primary transport.
Thanks.
Thank you, Pat.
Hi, Sherry.
This ends the session. Thank you. All right, next presenter is Kevin Chu from AMD. He's going to presenting AMD Pensando Pollara 400 AI NIC architecture and application. Kevin is a senior fellow at AMD's Data Center Networking Technology and Solutions Group, where he has co-led the architecture of multiple generations of Pensando P4 devices. Before joining AMD, Kevin spent over 15 years at Cisco. He holds both a bachelor and a master's degree in computing engineering from Boston University. Welcome, Kevin.
Thank you, Sherry, for the introduction. Hello, everyone. I'm excited to be here today on behalf of our teams at AMD to talk about our Pollara 400 AI NIC, a programmable NIC specifically designed for AI scale networks. Staying close with our customer has always been our highest priority. While we were delivering our DPU solutions to our front-end network customers, our customer come to us and say, you have a very good solutions for the front-end network, but we are also building this high-performance back-end networks, and we are facing quite some challenge there. Would you be able to help? Of course, we are eager to help. So we set out to analyze the fundamental issues faced by those scale-out back-end networks and what it takes to address them. We didn't stop there. We understand that this is a highly dynamic and fast-changing environment, so we want to provide the most flexibility and the highest performance for our customer. To do that, we leverage our expertise in the programmable architecture together with the knowledge of the specific issues in these AI scale networks and deliver this cutting-edge Pollara 400 AI NIC, which I'm going to go over the details in this presentation. Before I start, let me give an overview of what we are going to cover today. We'll first start with an introduction of our Pollara 400 AI NIC, followed by the details of our Pensando P4 architecture. We're going to cover several enhancements we make specifically in Pollara. And after we have a better understanding of our device architecture, we're going to start switch gear and looking at the application side. Specifically, we're going to look at several scale-out network challenges and the solution provided by UEC. Just in case you're not aware of UEC, UEC stands for Ultra Ethernet Consortium. It's a work group where all players, hyperscalers, and vendors all get together to address the biggest challenge facing the scale-out network, which AMD is a founding and contributing member. Finally, I'm going to show how Pollara 400 AI NIC is UEC ready, and the resulting performance gain by leveraging this unique architecture. We can implement new algorithms, adapt to new approaches, and for customer-specific or standard-based. This is the most flexible device at line rate speed, which no one else can deliver. For those who are not familiar with our AMD data center solutions, AMD offers the full solution space with EPYC CPU product line and Instinct GPU product line and Pensando product line for networking. Pollara 400 is part of the Pensando product family, specially designed for AI scale-out workloads. Here's an overview of our Pensando Pollara 400 AI NIC. It has fully programmable hardware pipelines, which you can leverage to get performance boost. It supports full 400 gig line rate. It's intended for an open ecosystem, and it's UEC ready. It helps reduce the overall job completion time, and it's built with high availabilities in mind. Let's start at the system level. Inside our GPU node, we have our Instinct GPUs connected with our AMD Infinity Fabric. Each of these GPUs are connected with our Pollara 400 AI NIC through PCIe switch. The Pollara 400 AI NIC provides the external scale-out connectivity to the Ethernet RDMA networks. Inside Pollara, starting at the bottom, we have our multi-speed MAC, followed by our P4net pipeline, which handles network processing functions such as packet parsing, table lookups, and packet rewrite. In the middle, we have our packet buffer, which handles the traffic burst. On the GPU and host side, we have our P4 DMA pipelines, which handles the RDMA transaction processing and the DMA transfer of data from packet to memory. The actual data transfer happens through the NOC and the PCIe interface on the upper left. On the upper right, we have our on-chip memories, which provide storage for our state and statistics, and it supports atomic update operations. Finally, on the lower left, we have specific logics such as doorbell handlers, hardware FIFOs, timers, and schedulers, etc. Let's take a closer look of our P4 pipeline. As seen from the previous slide, we have two versions of our P4 pipeline. The difference is that the start and end of the pipelines. The pipeline on the top is our P4net pipeline. It starts with a programmable parser, followed by 8 identical processing stages, and ends with a deparser. The pipeline at the bottom is our P4 DMA pipeline. It supports traffic in both directions. For the traffic for the TX traffic, it starts with the doorbell, scheduler, and followed by these 8 processing stages, and ends with an TXDMA engine. On the RX side, the packet comes in, first go through the splitter logic, then the same 8 processing stages, and ends with an RX DMA pipeline. Between these pipelines, we have a programmable data structure called PHV, packet header vector, which is used to carry the context information for the transactions passing through the pipeline. Let's look inside the main components of a pipeline stage, the TE and MPU, before we come back to look at the overall operations of the pipeline. Table engine. The main job of the table engine is to generate key from the PHV. decide which table to look up, perform the lookups, and pass all of this information to the MPU. It handles the control flow and table definition part of the P4 language. On the diagram on the right shows the key formation part of the table engine. In this particular case, we are forming 4 different keys in 4 different colors, and the component of the key can be scattered in different parts of the PHV. Once a key is formed, we can generate the lookup addresses based on anywhere in the key, any part of the key. In terms of table lookups, we support hash table lookups, direct index lookups, or TCAM lookups. And for the target, we support the local SRAMs, local TCAMs, or even host and GPU memories. Moving on to MPU. MPU stands for Match Processing Unit. It's a domain-specific processor which is designed to support efficient field manipulations. It takes the key and table data and the instruction starting address from the table engine, and it can start the execution as soon as it's launched. Besides the normal opcodes which you expect, such as ALU, branch, load store, it has specific domain-specific instructions such as PHP write, table write, and some custom instructions. Instead of a single memory, instead of a single data interface, it has separate memory, table, and PHP interfaces to avoid any contentions. Coming back to the P4 pipelines. For the P4 NAT, incoming packets first go through the programmable parser, where the packet header will be decoded and extracted into a PHV. At the same time, the original packet will be sent all the way down to the deparser and stored there waiting for the packet edit instructions. The PHV enters the stages and is going to perform the table lookups and action part of the P4 code. For the P4 NAT, it's typically network forwarding table lookups, and the action usually update the packet editing instructions. Once the packet editing instructions reach the deparser, the deparser is going to execute those instructions, update the packet, and send the packet out. For the P4 DMA, on the TX directions, the process starts when the host or GPU rings the doorbell of a particular queue, indicating that there's some work to be done there. So the doorbell engines pass that information to the scheduler. When the scheduler decides it's time to service that queue, it's going to generate a PHV with that particular queue numbers in the PHV and send it down the pipeline. The P4 pipeline, within the pipeline, we are also doing lookups and action part of the P4 code for a different program. In this particular case, the lookups are typically queue state informations, work queue request informations, descriptors, or scatter gatherers, and the action is updating the DMA instructions. Once the DMA instructions reach the TXDMA engine, it's going to execute those instructions, which can transfer data from the PHV or any memory locations to the outgoing packet or any other memory locations. In addition, it can update statistics, generate interrupts, or even ring the doorbell of a different queue to trigger additional processing. On the RX side, packet comes in with going into the packet splitter, where the packet will be split into, part of the packet will be split into the PHV, while the rest of the packet will be sent down to the RX DMA pipeline directly, waiting for the RX DMA instructions. The PHV go through the similar process with our RX DMA pipeline P4 programs. Once the DMA instructions reach the RX DMA engine, the RX DMA engine will also execute those instructions. In terms of instructions, the main difference is that RX DMA support sourcing data from the incoming packet, and it does not generate any outgoing packets. We now have covered the basic building blocks of our P4 pipeline architectures, and let's go over several enhancements we make in our Pollara. The first enhancement I'm going to cover is virtual address to physical address translations. Address translation is needed in most RDMA operations where the address given are all virtual, while we need the physical address to access physical memories. Since this function is well-defined and critical for RDMA operations, we have introduced special logic to handle this function in our P4 DMA pipelines. This function supports per logical interface, per memory region keys, page tables. It supports different page sizes and up to 5 levels of page tables per key. The state, registrations, and mappings are all controlled by software. The second enhancement I'm going to cover is our atomic operations. For certain well-defined atomic operations, we have implemented the logic right next to the memory. These functions can be implemented in our P4 pipeline stages, but having them right next to the memory greatly improves their performance. We support like counters, atomic vector set clears, atomic read increment, read decrement, and we even support metering our operations with token bucket updates as well. The last enhancement I'm going to go over is our pipeline cache coherencies. There are a lot of cases where data structures need to be shared and updated by different parts of the pipelines. A good example would be between RX and TX, where we need to keep track of the RDMA queue states of a particular queue pair. In Pollara, we have enhanced our coherency mechanism with a broadcast invalidate update network, which minimizes the time it takes to maintain our pipeline coherencies. It can be enabled on an address range basis, and it supports direct data update as well. This wraps up our overview of our Pollara AI NIC and our P4 architecture. Next, we are going to move to the application side. Specifically, we are going to look at several AI scale-out network challenges, and Pollara's unique programmability can be leveraged to address them. Let's take a step back here. Our goal is to improve the overall AI system performance. Here's just several data points showing the importance of the scale-out network. From the OCP keynote from Matter, on average, 30% of the training cycle time was waiting for networking. And from another paper with our teams at AMD, 40 to 75% of the time was spent on communication for training and distributed inferencing model. The exact numbers is less important here, but it's clear that the scale-out system is it's a major factor in the overall AI system performance, and we do need to optimize it. So data center has been around for a while. Why are we facing all these new challenges in the AI scale-out network? The main difference is network utilizations. From the Alibaba Cloud paper, general purpose network utilize less than 50% of the available bandwidth, while AI backend networks drive sustained data transfers and use almost the full capacity of the network. We can no longer just throw bandwidth at the problem. We need to optimize our network utilizations. To do that, we need better load balancing, congestion control management, and loss recovery. Let's look at each one of these challenges in more details. The first challenge I'm going to cover is load balancing. Traditionally, load balancing is done with static flow hash ECMP, where each flow assigns a different specific path in the network by static hashing. As all of us know, collusion do happen in hashing. When you have a large number of small flows, the collision is less noticeable because it's kind of random and short-lived. But when you have a smaller number of large flows, the collision can drastically reduce your network performance. Here in the diagrams, we are showing several potential collision points, and your performance is going to degrade based on the worst case, worst congested link, while you still have all of the available network capacities underutilized. One solution is to implement packet spraying with reordering, which we are going to cover later in this presentation. The second challenge I'm going to cover is congestion. Congestion do happen with traffic bursts and different traffic patterns, and which can lead to congestion spreading and really reduce your network performance. There has been quite a few different congestion control algorithms proposed for general data center network, such as DCQCN, but the reactive nature and difficulties in tuning them has led us to look for better algorithms. A recent algorithm used round-trip time-based feedback to dynamically adjust the transmission rate, which show promising results, and we are going to cover that later in the presentation. The last challenge I'm going to cover is packet loss. Packet loss due to buffer overflow or link bit errors can cause significant of retransmissions. The RDMA does provide reliable transport with the sequence number and timers, but it's using a go-back-N retransmission strategy, which has a very high cost every time retransmission happens. To avoid that steep penalty, strategies such as selective acknowledgement and retransmissions can be deployed. To address all of these challenges and many others in a consistent and open manner, Ultra Ethernet Consortium was formed. Members from different industries has all contributed their expertise and put in a lot of hard work in the past 2 years, and which UEC 1.0 specification was released in June this year. Instead of waiting for the silicon development of a new UEC device, we can leverage the benefit of UEC today with our Pollara 400 AI NIC. In the next couple of slides, we're going to go over several solutions based on our DMA with UEC transport, which we have implemented in our Pollara 400 AI NIC with our P4 programmable architecture. The first one I'm going to cover is multipathing. Previously, we have shown the issues with flow hash ECMP. UEC offer a recommended solution to address this issue. Instead of hashing, packets are sprayed into different paths of the network by assigning different entropy values. The entropy values are carried in the UDP header or the UEC entropy header. In addition, the system keeps track of the states of each individual path based on the feedback information in the reverse directions. This feedback mechanism allows us to identify and avoid congested paths, optimizing performance, and enhancing our reliability. Here's a small P4 code showing how this is implemented. We keep track of the path assignments and the path state in a table structure, which we will look up in our P4 DMA pipeline. In the action part of the code, this is where the actual packet spraying is done, where we actually assign different entropy value to the UDP source port number, while avoiding the congested path based on the state that's updated from the feedback in the reverse direction. On the receiving side, this is where we are updating the path status. We can access the same table entry, and in the action part of the code, we took the feedback information from the packet and used that to update the corresponding path status in the table entry such that the TX can avoid those congested paths. The next one I'm going to go over is congestion control. It's a transmitter-based congestion control algorithm. It measures the network-wide round-trip time, and it uses that to adjust the transmission window size, while taking into consideration of explicit events such as nags, ECM mark, or trim packets. In terms of P4 code, we have a table definition which we keep track of the multiple sequence number, such as the maximum, the TX, and the unnext sequence number. In the action part, if we detect that we are exceeding our window size, we are going to disable the scheduling of this particular queue and start a timer process where we'll restart this particular queue at a later time. This effectively slows down the transmission rate, which helped avoid putting more traffic into the congested network. On the receiving side, that's where we are updating the window size. So we can access the same table entry, and then if we don't have any explicit congestion events, we can increase our window size based on the round trip time compared to our baseline. But if we do have the congestion event and we are exceeding our delay target, we will decrease our window size to slow down the traffic. The last UEC solution I'm going to cover is selective AG. To implement selective AG, instead of sending a sequence number back from the receiver to the sender, we actually send a bitmap indicating both of the receive and transmit and the receive packet and the missing packet. Once the transmission side get that bitmap, it can figure out which packet are missing and only retransmitting those packets instead of retransmitting everything from the first missing packet. On the receive side, we keep track of the sequence number state in the bitmap in a table. The action part of the code actually set up the selective AG message contact and ring a doorbell on the transmission side so that we can send back a message back to the sender. On the sender side, when we receive this packet, this bitmap, we're going to look for any holes in the packet, any holes in the bitmap, and set up the boundary for retransmissions, and then we will actually ring a doorbell and start the retransmission process. After we put in all of these UEC solutions together into our P4 program, we're ready to see the performance comparisons. In this particular case, we are comparing standard RoCE v2 with our Pollara UEC-ready RDMA. Depending on the exact number of queues in the RoCE v2, we can see between 25 to 40% performance gain in all of these different message sizes. This is impressive. It's the same hardware that we use, but we can get such a huge performance gain by just leveraging new algorithms with our programmable architecture. All right. Let's do a quick summary. We covered the Pollara AI NICs and our P4 architectures. We cover several enhancements we make when we can continue to improve our P4 architecture. We cover several AI scale-out network challenges and the solution provided by UEC, and we see the performance gain from utilizing the UEC solutions with our programmable architecture. The key takeaway here is that Pollara is the first UEC-ready AI NIC, which resolves AI network challenges by leveraging solutions from UEC with our programmability. Just want to say thank you. I know I'm running out of time.
All right, thank you, Kevin. So we start the Q&A from the Slack channel. We do run out a little bit of time, so perhaps not too many questions. Slack channel first.
Yeah, this question is on the product lineup. Can you explain the difference between Pollara 400, Salina 400, and Volcano 800 in terms of their intended use cases?
What I can say is the Pollara 400 is intended for our AI scale-out network NICs. The Selena is actually our DPU product line, which handles the front-end network. And I cannot comment on Vulcano.
Okay. Questions from here?
George Kozma from Chips and Cheese. I'm just wondering what workloads would benefit from cache coherency via the P4 pipeline. Like, what workloads are you targeting with that?
We're not really targeting specific workloads. It's really when you have any kind of stateful operations between the pipelines, where because of the pipeline, we do have cache in there to improve the performance. So you need to keep the pipeline data structures coherent. So that's where we are actually, the pipeline coherencies is very important. Otherwise, you'll have to wait a lot of time just maintaining that coherency.
Okay, thank you.
No problem.
Question from here?
Hi, Kimbo from Semi-Analysis. So what is the latency throughput that a 12-stage doorbell lookup pipeline is?
I don't think I can answer that question.
Okay, so one final question.
Okay.
So I was wondering what the reason is that the Pensando NIC is using 112G Broadcom SerDes instead of AMD's in-house one.
How is our Broadcom NIC? You know better than me. I'm kidding. I'm wondering if I don't think I can. First of all, I don't think I can really comment on which particular SerDes that we are using. Which I'm kind of surprised you actually get that information. So I don't think I can really comment on that.
All right.
Okay, thank you.
Okay, we perhaps have a question for the last question. Select channel, perhaps.
Yeah, so this question is from Owen. The SDK used to program Pensando DPUs was previously open source. Do you have plans to make it open source again?
I think you need to pose that questions maybe to Slack channels, and I would need to consult with our other teams to see what's the plan there.
Sure, thanks.
Okay, so we run out of time, but you can still ask questions after the section. We will be in this corner. Thank you, Kevin.
Thank you.
All right, our next section is presented by Idan Burstein. We'll do the NVIDIA's ConnectX-8 SuperNIC. Idan is the Senior Director of Architecture at NVIDIA. He joined Mellanox in 2012. He is driving the architecture of ConnectX and Bluefield products. Idan also chairs the IBTA technical work group, where he leads the definition of InfiniBand and the RoCE specification and ecosystem enablement. Welcome, Idan.
Hi, everyone. So the slides. Okay. Hi, everyone. I know it's late. So I've been dealing with network adapters for a while. This is pretty fascinating space for me. Connecting compute and networking and algorithms all together into one solution that drives eventually computing in the industry. So I'm going to go through a component level discussion and then walk through how it affects applications, data centers. And then I'm going to end with a demo where I'll show some performance results from a real cluster in NVIDIA. So keep tuned. So I'll start with talking about AI for a moment. So we have these two distinguished workloads, inference and training, where training have this basically It's a synchronized, long-lasting workload that needs to scale to a lot of GPUs. So think about a 100K GPU cluster, where all of these GPUs are synchronized and are running one job. So every mistake in the synchrony can result in a very big impact on the network. Like think about events of 1,000 GPUs sending to one GPU, right? Think about the case where we all end this talk and go to the restroom, right? And then we stand on a line for a while and we wait and we waste all of our compute resources. It's a similar thing, right? So this creates an inefficiency that can affect our ability to train models and our ability to scale the models. Second is inference, where in inference, the response time need to be something that human can absorb, and it should be deterministic. And it also needs to be very efficient. So it's, you need to allocate the resources on the cluster, and if you have a good network, then you can allocate the resources as you want. And if your network has challenges on routing or on congestion control, then you need to basically manage your resources more tightly, and this leads to an inefficiency. Okay? So this is the problem that we are dealing with right now. And I'll try to capture how we solve this problem end to end, from a component to a full data center. So I'm here to present to you guys ConnectX-8. ConnectX-8, it's the first 800 gigabit per second NIC. It embeds a technology that is deployed over millions of GPUs. So previously, ConnectX-7 and 6 and 5 and all of these products were used for AI for a long time. It has an 800 gig RDMA pipeline. It's designed for bandwidth, latency, and scale. It integrates a load balancing and congestion control and reliability schemes that are designed for AI, which I will speak about a bit later in the talk. It has deep programmability because the workloads are changing, the clusters are changing, the networks that we are building are changing. We need deep programmability, and we basically keep optimizing the network by programming algorithms over the device. It's tightly integrated to the system, which is a critical component, like connecting to the GPU system, connecting to a CPU system efficiently, and it has enterprise class security, for example, network crypto and isolation. So here I'm going to speak a little bit about the details. Like it's an 800 gig product. It supports 800 gigabit per second InfiniBand and Ethernet, and it integrates the Ethernet, the Spectrum X Ethernet switch. And I will explain in later slides why we do that. It also integrates a PCA switch, which I'll explain why we do that as well. And it's basically the first deployment of PCIe Gen 6 together with NVIDIA GPUs. It has a line rate RDMA transport implemented by hardware with out-of-order delivery to deal with the fact that network workload needs to be distributed, as mentioned in previous talks. And it has interfaces with programmability to make the algorithms of controlling the network, like congestion control, reliability, retransmissions, routing, flexible. It has two kinds of processors that are programmable. One is called DPA, which I'll explain deeper in later slides. It's an event processor for processing events of networking. You should think about it as the server that is inside the NIC. And it has also a packet processor for basically programming the routing protocols, the encryption, the isolation, all of the services that can happen on a packet level, or implementing any kind of flexible packet processing that is needed in these systems. So this is just a glimpse on the performance. Like basically what we are targeting at is we need to be in line rate on all of the relevant message sizes and scales of queue pairs. This is a real measurement from a real ConnectX-8 system. This is basic RDMA write performance. You should think about it as the ping of the GPU networking. Okay, transferring bulks of data, 800 gig receive and transmit up to scale of 4K queue pairs. Then you start measuring collective performance. So these measurements are measuring a collective operation over multiple GPUs, doing all reduce and all to all, which is a common collectives that are used in inference and training in the east-west network. And you can see that on the relevant sizes like 24K, 256K and forward, we basically do line rate on these collectives, assuming that the network is non-blocking, which is the situation in this benchmark. Now I want to move into how we integrate into the system, which is something really important on designing network adapters. Network adapters today are not just NICs. They are basically, so traditionally it was a card that you push into a server, like with the gold fingers, and you plug a cable and it's your networking device, and there is the operating system that operates it, and there is the PCI switch that routes it. Today, basically the data center is the unit of computing. If you would be able, you would put all of the ASICs together and sort of let them work, right? But physics doesn't allow us to do it. So what we do is we build systems like GB300, where it's a dense system that is packing GPUs, CPUs, network adapters, switches, and NVLink switches. And basically, now this network adapter is not just a network adapter. It's now basically the ASIC that sits in the front of the server. So it needs to do all of the services that are needed in the front of the GPU server. So for example, for GB300, it needs to support PCI switching of Gen 6 in order to connect Gen 6 at high bandwidth, and to provide services to the communication libraries, and to the programmers which program on Docker. And for the network, it needs to also get connected to the network in a way that would be efficient to build a data center. And for that, it brings basically an integrated switch, which I'll talk about in later slides. It provides parts of the adaptive routing mechanism. Basically, the distribution of networking in the fabric is also assisted by the NIC, and it also does the congestion control for the network. So you should think about it as a device itself. The device itself is also serving a server and serving a network to build a data center. And this is the reason we basically do all of those stuff. So let's start with the PCI switch. So today in GB300, the ConnectX-8 is switching the PCI Gen 6 interface that is exposed by the Blackwell Ultra onto basically networking, connectivity to the Grace compute, and connectivity to SSDs. So you should think about it as sort of the south bridge of the GPU, and it's basically enabling the I/O speed to the Blackwell Ultra. Next I want to talk about is about the ConnectX-8 integrated Spectrum X. So basically in ConnectX-8 we have introduced this capability of supporting multiple planes. So the way we do that is the following. If you would connect a traditional NIC, you would connect a single port that is, for example, consuming 4 SerDeses or 8 SerDeses into a switch as one port connectivity. And then you would utilize basically 8 SerDeses of the switch from the switch radix, right? So if you do the math, you would end up with if you take a switch of 512-port radix, 512 SerDes radix, then if you do the math, you would end up with connecting with a non-blocking two-level FAT tree, connecting only 2K GPUs. Because every GPU would connect to 8 SerDes on the leaf, and then leafs would connect to the spine also with 8 SerDes, and you would end up with 64 times 32, which is 2K GPUs. What we do with ConnectX-8, we integrated the switch, and with this integration of the switch, we basically bifurcate the ports into different switches, so we consume less ports from the radix. So basically, you should think about it as the ConnectX is connected now to up to 8 different networks, which in every one of the network, it consumes only 1 port of the radix. And that is resulting in building a system that is non-blocking with 512-port radix of 128K GPUs. So it's a 64x scaling due to integration of a switching mechanism inside the NIC. Okay, that's a pretty strong thing, and now people can actually build a 128K GPU cluster in a non-blocking fashion. So this switch is pretty complex because it's a switch, but it needs to receive 800 gig and distribute the traffic over 8 ports of 100 gig or 4 ports of 200 gig. So it requires a very sophisticated RDMA transport on top that could deal with the out-of-orderness and reordering and do all the congestion management calculation and the adaptive routing calculation, which is something I'm going to describe in later slides, okay? So, I want to present the RDMA implementation of ConnectX-8. So, ConnectX-8 is basically the 8th generation of the RDMA developed previously in Mellanox, now in NVIDIA. It's basically, it's a multi-layer innovation. You should think about it as part of it is replacing operating systems, part of it is replacing hardware mechanisms for page translations, part of it is replacing a software stack like TCP. So the layers, you basically get descriptors from the application, you do quality of service, you do, you implement the application interface, which is, I want to send an RDMA write or an RDMA read or a send operation. Then you do the GPU or CPU memory access, which is a complex translation mechanism, as was discussed in previous presentations as one of the challenges, right? We do all of that in hardware. And then you basically need to do packetization and send it to the network or receive from the network. And here there's a lot of magic of how you do congestion control, how you do routing, how you do retransmissions. So we do all that by a hardware pipeline that is extremely efficient, that is transferring these descriptors into packets, as you've seen in the performance results. So this is the RDMA part of the pipeline. Following, we have the packet processor part of the pipeline, which is doing packet-to-packet manipulation. This processor receives packets and transmits packets. And it can pipeline operations on top. So for example, it does here the routing of spectrum mix, the collection of telemetry of spectrum mix, the network crypto, and the network virtualization. Okay, so it's a specialized crafted packet processor for these kind of operations. And you can program it with its internal instructions. Now, next, we have the DPA. The DPA is a cluster of 16 core, 16 threads, RISC-V processors. And this DPA is the brain of this machine. So the DPA receives events and return events from and to the pipeline. And it can do all of the math work. So you could think about within this pipeline of networking, You could think about algorithms like congestion control, algorithms of routing, algorithms of understanding a specific flow, metering flows, telemetry of flows. All of this stuff that requires math would go through this processor as the programmability that is embedded inside the NIC. You should think about it as the server that is inside the NIC that is basically doing all of the algorithmic programmable stuff that is needed inside the NIC, and I will show some examples later in the slides on how we use it. So I want to speak a little bit about congestion control and routing. So routing, you should think about routing as like I want to reach from point A to point B on a given network situation. So say that like for example, I think the best example for it is what you do when you go to the car and you route with Google Maps, right? So there is a situation inside the road, and Google Maps is finding the best location, the best way to get you to your location with the existing situation on the network. That's routing. Congestion control is a different mechanism. It's a mechanism where you are trying to prevent the network from being congestion by staying at the endpoint. So the equivalent of that would be staying in your parking lot if the roads are too congested. And the best example for that is in Israel, we have one ski resort that is open for 3 days. Okay? So when you come to this ski resort, it basically takes you like 5 hours of congestion, and eventually everyone gets in, right? So if there was an application that would, tell everyone when to come, no one would wait. So this is the mastery of congestion control. How do you deal with a network situation like many wants to send to one, or the network is oversubscribed, and you clean the network so everyone would wait on the edge, okay? That's congestion control. And there is also failures in the network, which is a sort of a combination of both of these problems, because when there is a failure, it creates congestion because it can create an oversubscription, and it also creates a routing problem because you may want to reroute stuff, right? So it's sort of a combination of both. Now, all of this stuff is mountains of software and hardware co-design. So it's the behavior of the switch, behavior of the ingest pipeline of the NIC, and behavior of the algorithms that you run on top. And it all needs to be resoluted very fast. So network round trip time today in AI clusters is like 5 to 10 microseconds. So you need to make this decision quite fast. A packet transmission time is like 2 nanoseconds, okay? So just to give you a ballpark of how much calculation you need to do in order to coordinate this system to be efficient, okay? So the way it operates in our device is that you have the RDMA pipeline, you have the packet processor. RDMA pipeline does sort of it orchestrates the transactions, it creates the trucks, right, that are going over towards the road. And the routing is sort of giving them, hints, go there, and both of these pipelines, which are complete hardware, are communicating with events and actions with the DPA, which is actually the brain. And there we run all of the algorithms. We decide on how to deal with congestion. We decide on how to deal with routing. We decide when to retransmit packets. And it's all coordinated with the switch capabilities of Spectrum X. And basically, we deliver all of this software as a complete package. So these are basically the results of this complete package. So you can see we improve like 1.6x in bandwidth that you achieve in higher bandwidth collectives. We improve latency in 1.3x. We improve noise reduction by 2.2x, and on this noise reduction I will show a demo in a while. And we basically can also provide very high frequent telemetry, which will be part of my demo. And it's all basically software stacks a lot of software stacks that are in between software on the switch, software on the NIC, tuning algorithms to make the data center work from day one at high performance. So now I'll move into the demo. So let's see. In this demo, we will connect to a cluster in Israel called Israel 1. And I'll start by showing basically what we do. We run on off-the-shelf Ethernet. We start with a basic NIC and a basic switch. And we run an LLM. And on this, we run an LLM. And on this LLM, we run additional workloads to basically create a noise. So you can see here in the active NIC count where workload 1 and workload 2 and workload 3 are basically generated. And you can see that once we generate another workload, the training step time is increased over time. See, from 15 seconds to 19 seconds. And if we zoom in basically on the network itself, you can see that the traffic on the network is not balanced. Like you can see that some of the queues are blown and some of the queues are empty, right? Let it move on. And this is basically the queue size of the switches. You can see that some of the queues are congested and some of the queues are empty and there's nothing going on there. And you can see that there is a lot of pauses and ECN marking for congestion control. And this creates a degradation in performance of 60%, which we've seen in the increase in step time. Now let's see what happens in Spectrum Mix. So again, we run an LLM, and then we add 2 more jobs to the LLM. You can see that the step time up there, it's flat, no change. So the LLM is running on 64 GPUs, and the noise that is added has no effect on the LLM step time. So 2 noises are added, and there is no effect. You can see that the training step time is basically maintaining as it was without any disruption. You can see that the bandwidth distribution across the ports of the switch is flat. There's no weird like this port is transmitting, this port is not transmitting. The algorithms have converged into a distribution of bandwidth which is flat. And you can see that the queuing is basically nothing. There's no back pressure to anything. And no TX poses, no RX poses, no ECN marking. And it's all these mountains of software, of algorithms in the NIC and algorithms in the switch that operates together. What needs to be centralized is centralized. What needs to be distributed is distributed. And we make the data center more efficient. Thank you.
Thank you, Idan. We can start Q&A from the Slack channel.
Yeah, we have a couple of questions on Slack. So this one is from Maya Gokhale. Can you describe the NIC memory system? What is it and how is it accessed by the compute resources on the NIC, like DPA and PSA?
Yeah, so the NIC has basically a centralized memory subsystem that all of the pipelines are accessing it on a cache line granularity, which is the internal cache line of the NIC. And we hold there the state of the queue pair, the state of the congestion, the state of the routing. And every pipeline has its own caches in order to operate in high performance if needed.
Hi, I'm Kantul Nalasway. So the PCI switch that you have in the NIC, is that fundamentally a fully functional switch, or is it basically all the ports are mainly communicating with the NIC itself and not between each other?
It's a fully functional PCI switch.
Hi, this is Yang Pu from BNP Paribas. Thank you for the beautiful presentation.
Can you repeat the name again?
Yang Pu from BNP Paribas.
Okay.
I have two questions, if I may. The first one is, one of your slides showed the performance of end-to-end Spectrum X performance. I believe that's ConnectX NIC to Spectrum switch back to ConnectX NIC. Do you have the, I wonder how compatible is your CX8 NIC to non-NVIDIA Ethernet switches? Like, do you have the same type of performance using ConnectX with a non-NVIDIA Ethernet switch?
So ConnectX-8 is an Ethernet NIC. Okay, it implements a standard called RoCE, and it can operate with any Ethernet switch existing. Of course, we tune our systems for our full end-to-end solution with Spectrum X, and that's the thing that will drive you probably the best successful integration when you build a cluster, right? But it can interoperate with any switch, and now it's up to you. You can program the algorithms, you can do anything. It's an open platform.
Thank you, that's fair. And the second question is, now with CX8 SuperNIC, sounds like it can perform a lot of load balancing, congestion control, routing functions. Does this mean that it could reduce the need of using deep buffering switches in the fabric to do the same routing, congestion control, load balancing functions in the fabric?
If I would design a data center, I would prefer the buffering to happen in the source.
Okay, gotcha, thank you.
Question from online?
Yeah, this question is from Frank Zhao. Can you clarify which processor architecture PSA is based on? Is it a RISC-V based architecture?
It's a custom. It's a custom architecture for packet processing. And DPA is RISC-V based.
This
is Song from AMD. Your previous generation ConnectX product had E-switches. E-switch. Now I don't see that. And then there's a Spectrum X. Is it replacing E-switch?
E-switch is part of the packet processor functionality. So it's another virtual workload.
So you still have the E-switch in it?
Yeah. Thank you. But we integrated, over here in CX8, we integrated an actual switch to do the multi-plane functionality, to distribute across ports, as I mentioned.
Hey, it's Frank Helms from AMD. First of all, awesome presentation. Thank you very much. Can you clarify what the simulation was? Was it like actually 3 training jobs running simultaneously, or was it synthetic, like all-to-all kind of pattern? What was the 3 things that were happening?
It was an LLM with 2 jobs of bisection bandwidth that basically creates a lot of bandwidth inside the network while the LLM is working. And it's there to represent the need, if you don't have this fungibility of dealing with noise, then you basically need to think about your allocation inside the data center. And this technology is enabling you to allocate your workload across GPUs however you want, right? It doesn't matter what other jobs are doing. You can utilize your cluster in 100% without having any fragmented allocations on your data center. That's the main reason we developed it.
Thank you.
So maybe very quick last question here.
Yeah, thank you. This is Saurabh here from Meta. You talked about the load balancing. Can you elaborate? Like, is that for ingress, egress, and at what level do you apply it?
So when you ingress on a NIC, you have nothing to do. You need to receive this packet or you drop it, right? That's the 2 approaches. When you egress into the network, you have a choice. And I was specifically speaking about the load balancing across planes, which I described earlier as the integrated switch that is, that can enable you to scale further GPU clusters. And also maybe making choices that are inside the network as well, right? Because you can provide hints. So,
thank you. Okay. I think that's it for this presentation. Thank you so much, Idan.
Thank you, sir.
All right, last presentation of the day. The last one is from Broadcom Tomahawk Ultra, will be presented by Mohan Kalkunte. Asad Khamisy will join the Q&A section. Mohan is Vice President of Architecture and Technology in the Core Switch Products Group at Broadcom, where he leads architecture for Ethernet switching and NIC products. With over 35 years of industrial experience, he holds a PhD from the Ohio State University and began his career at AT&T Bell Labs. He has served several patents, was named a Broadcom Fellow in 2009, and elected IEEE Fellow in 2013, NAE members in 2025, for his contributions to Ethernet switching. Asad is the Vice President of R&D in the Core Switch Products Group at Broadcom. As the head of the engineering team, Asad is responsible for developing all Broadcom network switching products. Asad has more than 25 years of experience in networking, communication, and semiconductors. He has begun managing the Broadcom switch product development since 2003. He received his PhD in electrical engineering from the Tel Aviv Israel Institute of Technology in 1994. Welcome, Mohan.
Good evening. I know it's been a long day. Hopefully you have some more energy left. I know we are the last presentation here, standing between the reception, if some of you are planning to go reception or planning to go home. So hopefully this will be of interest to you. The last three presentations were about NICs. So today we're going to talk about the switch. So we are really excited about Tomahawk Ultra. So this was launched a couple of months ago. And Tomahawk Ultra is a low latency, purpose-built switch for HPC and AI scale-up fabric. Now wait a minute. It was purpose-built for HPC to begin with. So approximately 2.5 years ago, we started thinking about how can you build an HPC Ethernet switch that has the characteristics of low latency and high bandwidth, high throughput. And what we have realized in the last year or so, that the characteristics of HPC fabric maps very well into the AI, into AI scale-up fabric. So if you look at the HPC and the AI workloads, right, pretty much there's a lot of overlap. But few things that kind of stands out. One is the small packet transfer or the small message transfers. HPC demands much smaller packet transfers, whereas I think within the AI scale-up, it can be slightly higher. Both of these, they need low latency, and I can hardly see here. Oh, I don't want to look up there, but I want to look up here. But anyway.
Can you make the screen bigger? It's very small.
So, in terms of bandwidth, right? In terms of bandwidth, both require high bandwidth, but the AI scale-up bandwidth from a switch point of view is growing much faster. From a scalability point of view, in case of HPC, you want to have several thousands of nodes interconnected or several thousands of switches interconnected. Whereas in the case of AI scale-up, it's a little bit more contained. You know, you have seen scale-up domains of 64, 72. We have, customers designing for 128, 144, and so on. We have started hearing about scale-up domain of 1,000 and even 2,000. And you will even see that we are hearing about scale-up domain where it is not just a single tier anymore, but it's a multi-hop kind of a tier. So this space, especially on the AI scale-up, is evolving very fast. So a lot of similarities in terms of topologies. The HPC topologies, you have Dragonfly, Clo, Mesh, Torus, and so on. AI scale-up, mostly what we see is the Clo type of topology, but there's also Mesh and Torus. But again, here we are seeing the topologies are also evolving for scale-up. So before we get into it, I want to address some of the common misconceptions that's out there on Ethernet. Ethernet has high latency. Typically this is what you hear, right? You hear all presentations, they talk about traditional Ethernet, and they say, oh, you can't use Ethernet because it has high latency, right? It does not have small packet performance. I cannot do line rate. So maybe I can do line rate at low bandwidth. Maybe I cannot do line rate at high bandwidth, right? So that's another common misconception that's out there. Ethernet is lossy, and it's not lossless, so you always drop packets. And the header overhead is very high, right? So if you look at the standard Ethernet header and IP header, it's about 40 bytes, right? Layer 2 plus layer 3 and so on. And when you have something that high overhead, and especially if you're doing small packet transfers, the common assumption is that it's not suitable. Now, all these things are true for commodity Ethernet, for general networking, but it's not so much true anymore for things like supercomputing or AI scale-up. So with that, we would like to introduce Tomahawk Ultra. So this is a 500 actually I have a chip here. So this is the Tomahawk Ultra that we are sampling right now. So it has 512 SerDes, 100 gig SerDes, PAM4 SerDes. It can be configured as, it has several configurations. It can be configured as 256 by 200 gig, 128 by 400, or 64 by 800 gig. All of these configurations are possible, and any combinations thereof. So let's look at what are the key highlights of this device, right? So one is, performance. In terms of performance, it's line rate performance for 64 bytes on all ports, whether it is 64 by, whether it is 256 by 200 or 128 by, no, maybe I'm getting it wrong. Yeah,
128 by 400.
128 by 400 or 64 by 800, it is line rate at 64 bytes, and that translates to about 77 billion packets per second. We also achieve a latency of 250 nanoseconds. I'll show you some of those charts later on. In terms of efficiency, we have what's called as the optimized headers. So this is one of the things that we have done here is like, because the Ethernet header overhead is much higher, how do you compress the information? It is not compression of the header. The header is still Ethernet. It's layer 2, layer 3 header. But the interpretation of that header is different, right? So we map the information onto this header, and that's what the switch understands. It supports reliability and lossless through LLR and CBFC. Another key features that we have is the programmable visibility and telemetry. We have extensive set of telemetry, especially where you want to look at very fine-grained metrics within the device. So that's something that, and as well as for HPC topologies. Topology-aware routing. HPC topologies are pretty complex, right? So, and also, even for AI scale-up, if you want to do mesh or torus and things like that. So we have built-in hooks into this device so that it can support all these different kinds of topologies. And I'll touch upon that a little bit more. And last but not the least, the congestion control. So congestion control, how does the switch expose some of these congestion metrics to the source so that the appropriate actions can be taken at the endpoint? So here's a simplified view of the pipeline. So we have many such pipelines in the device. But basically, the whole idea here is how do we make this very simple, right? Because of the line rate performance that we need to achieve, and because of the latency that we need to achieve, the pipeline had to be extremely simple. But having said that, it still has, like for instance, the parser. It's very optimized for, small packets. The forwarding lookup is all streamlined for deterministic processing. You have the filter processor if you want to do any kind of ACLs. And then we have the adaptive routing engine. Now, in Broadcom devices, we had adaptive routing for over a decade. It's just that we did not call it adaptive routing. It's called DLB, or dynamic load balancing. So I'm going to use the term adaptive routing and dynamic load balancing interchangeably. We have a collective offload engine built into this, and I'll talk a little bit more about that. And then there is a centralized telemetry visibility engine that looks at the various metrics within this device, and it can do summarization and things like that. And then we have the traffic management, or the buffer, where the queuing, the admission thresholds, the QoS, the scheduling, and all of that stuff is done. So this is a very simplified view of the pipeline. We have many of those built into the device to get the appropriate performance. So these are the key foundational features that are in the device, and I'll go through every one of them. The LLR, which is the link level retry and the credit-based flow control, optimized header, in-network collectives, topology-aware adaptive routing, the congestion control hooks in the device, the programmable visibility, and also finally talk about a little bit about the performance. Now, together with all of these capabilities, what makes the Tomahawk Ultra a switch for HPC and AI scale-up. So let's go one by one. Link level or link layer retry. So some of you might know about this, but basically, in traditionally in Ethernet, if a FEC error happens, then what happens is, that packet gets dropped, and then you need to have a higher layer or an upper layer to retransmit that packet. In case of link layer retry, what we're going to do is we're going to short circuit that so that at the link layer itself, you have a retry mechanism. So on the left here, you see the picture. This is like the IEEE 802.3 kind of a picture. You can see the MAC layer and the link layer. And you can see that the link layer retry is an optional layer above the MAC control layer. Okay? So the idea of link level retry is it improves the link robustness. So if there are bursty errors or any other suboptimal links or things like that, you can recover from that pretty fast. And basically, you're avoiding the need for high latency, penalty because of end-to-end transmissions, retransmissions. So how does it really work? So you have a transmitter and you have a receiver. The transmitter, sends packets, and in the Ethernet preamble, you carry a packet sequence number. Okay, these are ordered sets. There is also a replay buffer on the link buffer on the transmitter side, and it stores the packet until it gets an acknowledgement from the receiver. There's also a timeout mechanism so that, if it times out, then the transmitter can retransmit that packet. On the receiver side, you're tracking the expected sequence number, and whenever you get an error-free packet, it updates a sequence number. But it sends an ACK back in that case so that the transmitter can release that link buffer. Now, this is also an ordered set that goes through so that it can preempt the packet while it's going through. So it does not interrupt the operation of the packet transmission, but it's sent as an order set. And if there is an error packet, a NAC is sent back so that the transmitter can retransmit that packet. So this way, this is like the fast transmission. So in other words, the error detection and retransmission happens in the order of microseconds or nanoseconds rather than at milliseconds. By the way, just to let you know, right? So I can't go back. The link level retry is a feature that was standardized in the Ultra Ethernet Consortium 1.0. So we are compliant to that feature. And so is the credit-based flow control. It's another feature that is standardized in the UEC 1.0. So rather than using the pause frame, which can result in head-of-line blocking, we have implemented this credit-based flow control. And basically, the idea is simple. You only transmit, or the sender only transmit if it receives the credit. And how does it get the credit? The receiver sends the credit if he has the buffer to accept the packet, right? So that's the basic principle here. So for each lossless class, the receiver, sends credit. There's a credit generator, so it sends credits back to the sender. The sender knows across all its transmit queues which ones have credit. It has its own scheduling mechanism, and then it schedules the packet, so there is no packet drop. Unlike in pause frame, if it is not well orchestrated, you could have some drops in some instances. So the sender only schedules packet if it has the credits. So next step is what we call as the AI fabric header. Remember I told you about the how you can compress the information. So just to give some motivation, which I talked about earlier, right? So there could be load store operations which are smaller payloads, and putting a 40-byte header on top of it can be wildly inefficient, right? Now, the standard Ethernet plus IP headers, they give you flexibility, but they result in large penalty, right? And for these transfers, wire efficiency does matter, so therefore, the overhead needs to be minimized. So if you really look, especially in a scale-up domain for that matter, all you need is very minimal information, right? So, what is the destination GPU or the XPU it needs to send? Where is it coming from? What is the source XPU? Maybe QoS, and maybe hop count, and so on. So it's very minimal information. So what we do is this AFH, that information is overlaid on the Ethernet MAC header. And you can choose. But by the way, this doesn't mean this is the only thing that the device supports. The device supports all the standard Ethernet headers, and we can have these headers coexist. So just, if you want to send traffic between the two GPUs, you can use this header. There's other control traffic, for instance, that can use a standard layer 2 header. So that's the whole idea here, right? So the address fields can be 2 bytes, 4 bytes. If you're just supporting, let's say, for instance, 1,000 XPUs in a scale-up domain, all you need is 10-bit identifier. The semantics of this, it does not matter to the underlying switch. Only the endpoints needs to know what the semantics of that. So what we do is we take this information and overlay on the header, right? And then overlay on the MAC header. So you can use rest of the bytes, the endpoints or the host in this case can use rest of the bytes to pack other information on top of it. So this is how we achieve the wire efficiency for the smaller packet transfers. Just a little bit more information here. Like I said before, there's a Gen 1 header. We support Gen 2 headers. And also, the latest one is the one in the bottom that I show there. That's, you can see the first 2 rows there is the MACDA. It's kind of a little weird the way it is shown here, 3 bytes wide. But the first 2 rows together make the 6 bytes. And the second 2 rows together makes the MAC-SA, which is the 6 bytes. And you can see that out of this, only 6 bytes are used. And the rest of the bytes can be used for whatever the host side wants to do with it. In Tomahawk Ultra, we also implemented this collective offload. Now, collective communication is bandwidth heavy, but the computation is, not that heavy. So switch is a natural place to put this. So when we started this, we decided to put this feature in, and we wanted to make it work with any endpoint, like any RDMA endpoint. So that's what we did. So the number of different collectives that we support, like reduce, all reduce, broadcast. We support number of different formats also, both floating point as well as integers. And we support both the push and the pull model, that is the RDMA read and write. So you can have a hierarchy of these switches. You can have a rack switch, you can have a fabric switch and a spine switch, and you can do a read from the root of the switch to all the GPUs. And as the GPUs are sending collectives up, they get aggregated. They go all the way to the root switch, and then the root switch does the final aggregation and then broadcasts it down. So this whole operation is supported in our hardware, as well as the associated software is also there. Okay, want to talk about the topology-aware adaptive routing. So let me build this slide up so that it's easier. As I mentioned before, we support all kinds of different topologies, right? Especially in the HPC case, right? Dragonfly Plus, CLO, 3D Torus, and so on. Unlike the standard CLO, right, where routing is very simple in a standard CLO, right? Paths are all equal. All you have to do is do the lookup, and you do the lookup based on the destination. But in case of topologies like mesh or Dragonfly and everything, you have to take some additional things into consideration depending on where the packet came in, or which source port the packet came in, or in which direction the packet came in. So for instance, in a mesh network, if a packet came in from west, then maybe it's allowed to go north and south. So you have to build those restrictions into the system, otherwise you will run into loops, right? So those capabilities do all exist in this device. We can do load aware and load unaware. We can do spraying, we can do flowlet, lots of different capabilities that we have. Fast failure detection, very flexible policies. And the nice thing about this is it's not all hard-coded. It's all highly configurable kind of stuff. Next, I want to talk about the programmable visibility, right? Now, in AI networks, right, the behavior is at microsecond level granularity. So if you want to observe things today, people generally systems they log in at milliseconds. So you can't observe these events at millisecond intervals when those happen at microsecond level granularity. Now this is one of the key capabilities in our device that we have. We have a very rich set of metrics. We have over 20 metrics within the switch, whether it is queues, queue length, delays, drops, counters, stats, all kinds of metrics that are distributed among the various switch components. And we have a compute engine built into it that can have fast access to all of these metrics, and it can do summarization. And the nice thing about this is none of this is hard-coded. It is completely programmable. So the user can specify exactly what metric to collect, when to collect, how often to collect. So all of that stuff is kind of, is a flexibility that the user has. So in terms of congestion control, there are two types. One is a proactive telemetry and the reactive feedback. Endpoints might be sending active probes to say, hey, tell me the health of the network. It might be, tell me the bottleneck, tell me the queue length, tell me the delay, tell me the residence time, and so on. And we support that through in-band telemetry, such as IFA, which stands for In-Band Flow Analyzer, or it can be something like a CSIG, which is a congestion signaling message. So there's the proactive telemetry, as well as the reactive feedback. So packet trimming is one of those features that was standardized in the UEC 1.0, wherein if a packet experiences congestion, instead of dropping the packet and the sender finding it out after some transmission timeout, you trim the packet, the header goes in a high priority queue to the receiver, and the receiver sends congestion notification back to the sender. So the whole idea here is, how do you get information out to this to these sources as soon as possible, not 2 RTTs or something. How do you get this information within an RTT? So that's the whole idea of these congestion control hooks. Here's a chart on the performance. So this one shows 800 gig ports all running at line rate. So you can see that we achieve 800 gig ports. So this is a testimonial to the fact that it's a line rate 77 billion packets per second. And here's another chart that shows what the latency looks like. You can see it's the latency is about there's a min max P99 and all of that stuff, but it is more or less than 250 nanoseconds in this case. I'm running out of time, so I'm going to fast forward. So just a few implementation highlights. First of all, it's a monolithic device. Why monolithic? That's the way to do it. If you can do monolithic, we always try to do monolithic. It helps in latency as opposed to having a multi-die. It helps in power, keeping the power low. The package, sorry, I can't even read. Package and power, okay, I'm going to build up this whole thing. So it's built in TSMC 5 nanometers, and it is pin compatible to our previous generation Tomahawk 5. So one of the nice things about this is we have customers already started development with Tomahawk 5, and we drop in Tomahawk Ultra into this. And the other nice thing about this is it has the DSP SerDes. This is what we call the Peregrine SerDes, the best SerDes out in the industry. It can drive up to 4 meters of DAC cable, twice the distance that is specified by the IEEE. And just to wrap up here finally, it's not a one-off thing, right? It's not like, okay, I'm just going to look at one particular device. But our goal, Broadcom's goal, is to drive Ethernet across the spectrum here. So whether it is scale up within the pod, that is Tomahawk Ultra. We also have Tomahawk 6. This is our 100 terabit device that we launched a couple of months ago. And interestingly enough, this is the first device with 200 gig SerDes, switch with 200 gig SerDes. And this is also being used for scale up by some of our customers. And scale out. And then we also announced a device called Jericho 4. This is a 51.2 device. Now you might have seen that some of these hyperscalers, they want to build data centers, but because of power limitations, they have multiple data centers which are spread by several tens of kilometers that they want to hook up all together. And this is where Jericho 4 comes into play, so that it has a deep buffer capability. It can support RDMA up to about 100 kilometers. So whether it is in the pod, across the pod, or across regions, we have Ethernet to cover the entire spectrum here. So just to summarize, I think we talked about all of these things. The Tomahawk Ultra, 77 billion packets per second, latency, lossless operation, improved link reliability, and and it's got built-in network collectives and so on. So with that, thank you very much.
Okay, we can start the Q&A section. Select first.
Yeah, this question is from Cliff Young. Do link-level retry mechanisms interact with data center congestion control schemes like timely, given that retries increase the round-trip time and could be misinterpreted as congestion by the timely scheduler?
Yeah, I can answer that. So the retry happens at very fast. It's at the nanosecond levels, right? It's not like it doesn't increase the delay inordinately. So I don't think it really impacts things like timely scheduler, because those schedulers are operating on a different time scale. This is at a much lower time scale.
Think about it like just reducing your bit error probability.
Yeah.
That's what it is.
Yeah, Joe Byrne, XPU.pub. I have two questions about the collectives. First one, when you're zippering flows together to do the collective, how do you synchronize the flows? Because you can't just buffer them. So is there a protocol for that?
Do you want to answer?
So we support both RDMA read and write. So as a switch, we can read from in GPUs. We issue the read transaction.
You pull it.
That's
yeah,
it. Okay. So we wait for them, the first packet of each message to arrive. We do the reduction, then we do the broadcast, and so on. So yes, they have to arrive roughly at the same time. The GPUs have to collaborate.
And then the second question is similar. Does anybody actually do this in practice?
Pardon?
Does anybody do collectives in the switch in practice?
Well, we keep hearing about it. There are
same here.
There are some customers that are interested in it, but we have heard with other implementations there's challenges in terms of stability and so on. There are some people who like it, some people who don't like it, but who are we to say, right? Hey, we'll put it in. If you want to use it, go ahead and use it.
Yeah,
customer's always right.
Yeah, I think one thing, the previous offering in the market for collectives was very low bandwidth. It was kind of, like a NIC that you go to and do it. This is full bandwidth. Okay, yeah. This is collective at full scale, full bandwidth. Okay, that's the difference. So we still, this product being have sampled, customers building systems. We are working with several customers. We'll see.
Hi, Nathan Brookwood, Insight 64. I have a simple question and a comment. The simple question is, what version of PCIe are you using for this? Is it still 5 or have you gone to 6?
PCIe?
Yeah.
We use Gen 5.
Gen 5?
Yes, four lanes of Gen 5 to the CPU.
Okay.
Yeah.
That was a simple question. The comment was, your whole presentation reminded me of something Bob Metcalf, who was one of the inventors of Ethernet, once told me. He said, the secret to Ethernet's longevity as the leading network technology is they put the label Ethernet on anything that really resembles Ethernet in terms of the frame structure. And I think you are making him a happy guy today.
Oh.
Another question from online?
Yeah, this question is from Finn, Ashley, on latency. Is 250 nanoseconds consistent between any two ports? Is it consistent for all features and flow types? And does it require AFH?
Yes, so it is first bit in, first bit out. You take a packet from the time the first bit hit the switch until the time the first bit leave the switch. That's the latency we measure, fully featured. Layer 2, layer 3, with AFH, without AFH, it doesn't matter.
Perhaps last question of the day.
Chester Lam from Chips and Cheese. I was curious about the link layer retransmit thing. You have a replay buffer for that. So how big is that buffer? Is it good enough for keeping like many jumbo packets in flight?
So,
Like
yeah, so we support, in 200 gig, we support 150 meters. And in 400 gig, we support 200 meters distance. That's the size of the buffer, basically. So if you have 200 gigabit per second transmission, okay, we have enough buffer to sustain the round trip for 200 meters.
Okay.
All right. Thank you so much, Asad and Mohan.